So in the second half of 7.2, we're going to effectively work up to being able to do these problems almost in the reverse order of what we were just doing earlier in 7.2. Now to get there, we need to look at a new calculator function. So another thing we need our graphing calculator for, because we want to be able to find z-scores that correspond to areas. Remember, normal CDF was taking in z-scores and giving out the area between them. We want to go in the other direction. So we have a calculator function in the exact same spot, second in vars. It was the very next option, inv_norm, stands for inverse norm. That function is designed to take in an area and spit out a z-score. Now specifically, what's important about that is it only works one way. You have to put in an area to the left of a z-score, and then that will spit out the value of the z-score itself. Okay, so that is the key. It must be the area to the left. That's the only way inverse norm will function. So a couple quick ones here, and then we'll get into the real, I'll call them again, official applications. So finding a z-score that is greater than 40% of the data values, make sure you read it very carefully here. Don't just see the word greater and think shade to the right. Finding the z-score that's greater than 40%, if we draw a quick picture here, quick normal curve, to say that the z-score is greater than 40% of the data values would be the same thing as saying the z-score has 40% of the values below it, right? The z-score is greater than that much. So if a z-score is greater than only 40%, think of it this way. Is that z-score even to the halfway point yet? Would that z-score be in the middle? No, because the z-score in the middle is above or greater than 50%, right? There's 50% of the data values below it. You want a z-score that's greater than only 40%. So our line to represent that would be somewhere to the left of center a little bit, because what we're saying is this place right here, wherever that z-score is, has 40%, 0.4, 0.40 to its left, right? This is the z-score that's larger than, right? Greater than, above 40% of the data values. So read carefully when you're reading any question and make sure you don't just default to shading the direction that the word looks like it shades. Read it very carefully. So all these are relating the z-score to the data values. Now, once you've got that picture drawn, notice for this picture, 0.4 is the area to the left of that z-score. So to find that z-score, all I have to do is go to my calculator and use inverse norm and simply plug in the 0.4. So again, it's the same menu, second and distribution, but then you go down to option number 3, inverse norm, enter, and all you do is you enter the area to the left and it spits out that z-score. Being a z-score, I'll go ahead and round it to 3 places. So negative 0.253. And notice, makes sense that it would be a little bit to the left of center. Center is 0, a little bit to the left, so a negative z-score value there. Okay? Next one, find the z-score that is less than 70% of data values. So again, with a bell-shaped curve here, I want my line to be drawn somewhere where it is less than 70% of the values, below 70% of the values. Or in other words, the z-score has 70% that are above it. Well, that means a lot of the data should be above it. Again, midpoint's 50%. I want more than 50%. I want 70% to be above it. I got to shift further left, somewhere over here, for my z-score, so that that z-score, that line, is less than 70% of the data. Here would be a good chunk, 70% of the data, and there's my z-score being less than all those values, right? Anything on the axis from here and above, representing 70% of the distribution, is above it. And so that area is 0.7. Now, if that area is 0.7, that's not the number we're putting in inverse norm, right? Inverse norm needs area to the left, so we can simply use our complement rule to say if 0.7 is to the left, then 1 minus 0.7, or 0.3, is to the left. I said left. 0.7 is to the right, so 0.3 is to the left, and that number is the number we want to put into inverse norm. Always has to be area to the left. So inverse norm of 0.3, giving me negative 0.524. And that makes sense. It's got to be a bit further left, because this z-score had 40% to its left and was there, slightly to the left of 0. This z-score only has 30% to its left, so it's got to be further to the left of the center, further to the left of 0. Now the last one, find the z-scores that bound the middle 56% of the data values. All right, so for the middle 56%, that's relying on us knowing that the bell shape is symmetric. And so the middle 56, it's hard to estimate exactly where this is going to be, but what I want to point out is I'm going to try to draw lines equidistant from the center, because when they say middle, they're referring to the same distance left and right of center. Now, because of that, if we're doing the same distance, I'm going to go ahead and put 0 in here for a moment. If we're saying this is a boundary and a boundary that are the same distance from 0, but we don't know what they are, I'm going to label this z and that negative z to represent the fact that they're the same distance, just in opposite directions. Now also, the middle 56%, it means that area is 0.56. Now again, that's not the area we're going to put in inverse norm. What we need is area to the left. Well, we're going to have to use this number to say if there's 56% of the data in between them, then 1 minus 0.56 or 0.44 would be what we could call outside of those two boundaries, right? Or the unshaded stuff. But that 0.44 should be split into two tails, which are also symmetric, which are also equal. So we take that 0.44 and divide it by 2, and we get 0.22, and I'm going to refer to this as in each tail. The word tail is the word you're going to see a lot here with this kind of picture again. 0.22 being the area in either of those tails. And I also want to point out again, I keep labeling areas above, right? Drawing these arrows or lines into the picture, leaving any values that represent z-scores or numbers below or on that axis down below. It's again a good organizational tool. Now, as far as finding them, the nice thing about this is as long as we find one, we know the other is just the opposite sign. I'm going to go ahead and say, let's take this one right here, because I can look at this z-score with that boundary line, and I can say immediately the area to its left is that 0.22. You could have done this one. The key would be with this one, you have to understand that there's all of this 0.56 and the 0.22 to its left. So this one's a little more straightforward. We can just throw 0.22 into our inverse norm and get a negative 0.772. And that was the negative, which makes sense, negative z-score, which means we also know that 0.772 would be the z-score for our positive z-score. And there are two z-scores that bound the middle 56%. The last example on this page here is just kind of making us aware of some notation that we're going to see going forward in different formulas. And that is that if you see a z with a subscript of a number, referred to as alpha quite often, but z sub alpha, this will be a decimal of some kind. This is a shorthand way of asking for the z-score with that area. Now, the weird thing is it's the area to the right. There's reasons for that. They're not trying to necessarily confuse you, but just understand that going forward, z sub alpha is a z-score with the area of alpha to its right. This picture describes that entire sentence right there. That's the z sub alpha because alpha, I'll even do that, alpha is to its right. Whatever alpha is, whatever decimal. So in this case, z sub 0.4 would represent a picture where there's 0.4 to its right. Now just think about where that line would need to go. If you want 0.4 to its right, again, that's not quite half. So here would be the line with half to its right. We want a line with only 0.4, so I'll shift it over a bit and say that here's my value of z sub 0.4, because that now is 0.4, or 40% of our data. And that is now something we can throw into inverse norm. However, notice again, 0.4 is not the number you want. Alpha, in this case 0.4, was to its right. We can subtract that from 1 minus 0.4, and realize that 0.6 is to its left. and that's the value we need to put into inverse norm. So inverse norm of 0.6, 0.253 if we go to 3 places for the z-score. So now all we need is a way to take the z-score that inverse norm is giving us and getting back to a data value. To get back to these word problems, these applications that have actual numbers and interpretations, we need to get back to the data value. Well, there's this formula right here that will do that. You can find a data value by simply saying you've got the mean, standard deviation, and the z-score, and plugging those in. I want to explain this formula a couple ways. First of all, this is a formula version of our definition of a z-score, because the definition was that a z-score is the number of standard deviations away from the mean that a value is. Well, look at what this says. If you have a z-score for a value that you don't know, you take that z-score times the size of the standard deviation, and then whether it's positive or negative would determine the plus or the minus, but add that to the mean, and that gets you your number. That's literally just describing that the z-score is the number of standard deviations away from the mean that a data value is. Also, interestingly enough, and that's what this blank is here for in your notes, there's our formula for z-score. This formula comes from that formula. Just doing a quick bit of algebra, multiplying both sides by the denominator to cancel it. Then you've got this side, which I'm going to write as z times sigma rather than sigma times z. That's been canceled, so you're left with that. And if I go to solve for x and move that mu over, you're going to get mu plus z sigma equals x. You basically get that formula from our z-score formula. So moving forward, here's a quick reminder of a terminology we learned a couple chapters ago, the word percentile. If something falls in a kth percentile, then you're talking about that value being greater than k% of your distribution, k% of the data values. So in this example, we have a class scores that follow a normal distribution. They give us the class average, the class standard deviation, and then the question. Find the score that would be the 34th percentile. So notice, just to compare real quickly, this question to the other questions in 7.2, we're not asking you for probability. We're not asking you for percentage or proportion, right? We're asking you for the score, the number, right? The value. That's what keys you in on. This is the question in 7.2 that is going in that opposite direction, the ones we were doing earlier. So for this, the steps are actually above on the page here. We're going to start with just one normal curve. That's all we need. We actually don't need 2 for this picture. And we'll go ahead and take this world and consider it to be z-score world, a z-score picture. Now, using what we just recalled of what the word percentile means, to be in the 34th percentile means you're at a value with 34% of the values below it. You're greater than 34%. So where would a line be that is greater than 34%? Well, it would need to be to the left, so somewhere over here, so that where it's at, there's 0.34 below it, right? That would be where a z-score value would fall, where a line would fall, that is 34% below it. So it is greater than 34%. So that's the picture. And now, to find that z-score, we can use that information. In fact, that's exactly the number we would want to throw into inverse norm. Inverse norm of 0.34 is negative 0.412. I'll go ahead and go 3 places here. Now, that I'm going to make sure I label. That's a z-score. Hopefully it's not confusing, able to be confused with a probability because it's negative. We know probabilities cannot be negative. We also know that inverse norm always gives a z-score. And now we will use that formula from above to say if I want to figure out what data value that z-score represents, then I will just plug in the mean of 75. You could write plus negative 0.412 or just understand that that's going to be a minus 0.412 times the standard deviation of 4. So we will see what that comes out to be. So I'm getting x equals 73.352. And so that value would be the score that would fit the 34th percentile. We're saying someone who scored there, which is a very specific number, but that value is the location where 34% of the scores are below that, 34% of the scores are below that, and 66% of the scores are above it, right? So the score at the 34th percentile is 73.352. There's not really units on this. They didn't give us units. We could assume these are percentages, perhaps, but we don't know, right? Maybe the grade were out of a 90-point test. We don't know. So I'm not putting units on that, but that would be the interpretation of that answer. All right, so for the next one here, to qualify for training, recruits are tested for their stress tolerance. We have normally distributed scores with a mean of 62, standard deviation of 8. If only the top 15% of recruits are selected, find the minimum score required to qualify. So again, we're given a percentage, a probability or proportion, and we're asking to find the location of the value of the score that separates that. So we have a normal shaped distribution. We want the top 15%, top 15, the best 15. They're up here. And 15% isn't a lot, so it's going to be a small tail, we'll say. We want to know where that value would be so that that area is 0.15. That's what this question's looking for. So if that's 0.15 and we're going to be looking to find the z-score, we're going to need inverse norm, but we're going to need area to the left. So if that's 0.15, 1 minus 0.15 would give me 0.85 as the area to its left. And that will be the number we throw into inverse norm. Giving me 1.036. Again, that represents a z-score, which is why it's a number bigger than 1 here. And then we'll throw that into our formula to get back to the data value. We'll find the data value where the mean was 62. The data value's z-score is 1.036. The size of a jump of a standard deviation is 8. And that's putting me at 70.288. So since we don't know whether or not scores can be decimals or not, we'll go ahead and just stick with this value, right? This would be the assumed score potential, because we're saying find the minimum score required to qualify. If you can get this number, right, if you can get to that score, you're at the top 15%. So we'll say the minimum score to qualify. Let's see, we're talking about for training. Okay, for training is 70.288. So one more example, and I like throwing this example in because I find quite a few students have an interpretation of this word that isn't necessarily completely accurate when we talk about grading on a curve. You can curve a test artificially by just adding points to it, but true grading a set of exams on a curve, or a set of anything on a curve, is actually from this idea of using an essentially normal distribution and saying that no matter what the grades are, forget percentages like 90 to 100 is an A, 80 to 90 is a B, instead just see where the scores fall and then break them into the different percentages of scores, meaning the lowest 3%, no matter what values they got, no matter what scores they got, the lowest 3% get an F. And only the top 3% of the scores receive an A. So then you're looking at these other intervals in between, they get the B's, C's, and D's. This is, if you want to call it true grading on a curve, which I think most students are probably thankful that teachers don't do. But here's the question. If the class average on an exam was 80, standard deviation is 6, find the lowest grade to pass the class, or pass the exam, rather. And we'll assume that means C or better. That's what passing would generally represent. So, with our picture, we can draw a bell-shaped curve. It didn't say it's normally distributed, but we're going to use the idea of normal distribution here with this grading on a curve to say we want a student to have a C or better. Well, look up at this picture. C or better is all of that. 74 and 10 and 3. So a total of 87%, right? 87% of the students are going to pass this exam based on following a grading on a curve. That 87% should represent the area to the right of that cutoff point. So I want a line pretty low so that this area to its right represents 87% of the distribution. And that's the z-score we want to find, which means that area that we actually need for our inverse norm is 1 minus 0.87, oops, so 0.13. And that tells us what we're going to put into inverse norm. Inverse norm of 0.13, giving me a negative 1.126. And then that we can throw back into our formula to determine what the data value would be represented by that z-score. We said the mean was 80, the z-score is negative, so I'll put minus 1.126 times the standard deviation, which was size 6. And I'm getting 73.244. And so we would say, based on that, the lowest grade to pass the exam is a 73.24.